Okay, so we defined partial synchrony. That was what we did before going for lunch. So now next question is, okay, so now we want to achieve synchronous rounds giving partial synchrony assumption. And an interesting thing is that essentially we already have a solution for this problem. So why? Okay, so the first of all, round synchronization can only be achieved after global stabilization time, right? Because before global stabilization time, we don't have any guarantees on timeliness of the system, so anything can happen. So it's futile to hope that we can synchronize rounds before that. Now, when we arrive at GST, the way to look at the situation that we're currently at is that essentially from this point here, we are back in the synchronous world, right? So, but what happens is that because of the asynchrony, processes end up accumulating a lot of skew in their clocks, right? Because clocks drifted, and or you can kind of think about it as though clocks drifted, and then you go to some arbitrary views here, right? So this, for example, this process got to view 4, this one also to view 4, and this one I think it's something like 25, right? But now we're back in the synchronous world. So what we can do? So we have an algorithm that can cope with the clock drift, or we can just run this algorithm, right? And we can pretty much synchronize, use this algorithm to synchronize the rounds, right? So of course we don't know when GST occurs, so we just keep running this algorithm in the background, and then once GST kicks in and there is synchrony, then this algorithm would guarantee that everyone gets synchronized, and they continue to be synchronized from that moment on. Okay. So that's an interesting lesson, is that you can essentially deal with partial synchrony using techniques which are completely synchronous, right? So that's was some interesting realization that I was surprising for me as well. So yeah, so this is what is written for you here. So any synchronous CFT round synchronization that can cope with clock drift can be used to synchronize rounds in partially synchronous system. Okay, so this is as it comes to round synchronization and partial synchrony. But the next question is, what about consensus, right? So now, of course, we have a problem of the following nature, that before GST, we can't rely on any kind of synchrony, right? So that means that the best we can hope to achieve before GST is safety, right? So we should not violate agreement before GST. And then we can rely on eventual synchrony for liveness. Okay, so that leads to something that I call a view-based framework, right? So it's not a round-based framework anymore. Okay, so instead I replacing rounds with views, and it's not just substitution, substitute round for view. So we gonna treat views differently from rounds. Okay, so view is just a way to extricate the processes from a situation where they don't have liveness. Okay, so before the next view occurs, the process essentially just needs to run a protocol which is asynchronous, right? So this protocol that preserves safety even during asynchrony, and then they rely on the view synchronizer giving them the next view, right? In case they can't achieve progress in the current one. Okay, so views are essentially going to be coarse-grained as compared to round. So remember that in a round-based system, we essentially synchronize on every message being sent, right? So this is a round. Okay, in a view-based system, we don't do this, right? So we essentially let protocols to run at a wire speed, if you want. Okay, and then if they are stuck, then there is a view synchronizer out there that would ensure that they are pushed out of that situation. Okay, so view-based framework essentially achieve what I said before, that that we need to ensure liveness is this separation between safety and liveness, okay, in the protocol design. Okay. Okay, so this I'm gonna skip, so we already know what safety and liveness is. So let's talk about partially synchronous consensus. Okay, so that's our next stop. So what is important about partially synchronous consensus is that it needs to satisfy agreement and validity at all times, including including before GST, and then termination only after GST occurs. So one question to you, if I can use floods. So we discussed this synchronous round-based consensus, which is called flood set. Can I use flood set to solve consensus in partial synchronous system? Yeah. Yeah, I can't use flood set, for example, because I don't know when GST occurs, right? So in particular, the first f+1 rounds may all occur, or f+1 views may all occur before GST. And important thing is that flood set relies on round synchronization not only for liveness but also for safety. So it's important that there is a view or round where everyone sees everyone else's value, right? And that can't be guaranteed with partial synchrony, right? So this kind of supports this idea why this separation between liveness and safety is important. And so we need to kind of depart from a round-based system and look at a more coarse-grained view-based system. Okay, so there, if you want to do some exercises again in your free time, then you can convince yourself that you can't fix a flood set in any simple way to make it work. And if you try to do this, you eventually arrive to something which is as complex as, say, Paxos or any kind of this, any type of this sort of algorithms. Okay. Right. Okay, so let's see how we build consensus in a view-based framework. So view-based framework actually was introduced. Yeah, so it was introduced first in this paper by Oki and Liskov in '88. It was called view-stamped replication. So this was the first paper to talk about views, more or less in the same sense as we are talking about them today. Okay. So then this is our paper, and then also there was a paper by Naor et al. So the people from I think VMware at that time. Naor, M is for Malhi, it's Baudet. Okay. Yeah, so they also discussed several view synchronizers for Byzantine consensus. So actually, our synchronizer that we developed is very close to what they call broadcast synchronizer. Okay. So how a view-based framework works? So we kind of divide the execution into views, so not into rounds anymore. So every view has a unique leader, so that can be established, for example, by a simple function. just take a remainder from the division by n. And then in every view, leader tries to reach a decision using something which is essentially an asynchronous protocol. Okay, so can't rely on synchrony in any way because we can still be in a asynchronous period. And if the protocol gets stuck, then synchronizer will at some point give us the next view, and then next leader can try, and so on and so forth. So the many reasons for why protocol can start before JST, for example, and because of the message delays, messages don't arrive on time, or a leader can be faulty, so that can be a reason even after JST. So this view-based framework, it actually allows us to never get stuck. Doesn't matter before JST or after JST. But what is important is that the protocol within each view should essentially be asynchronous, right? And the reason for that is that picture is not as simple as it appears here. So before JST, we can have, like some really wild situation with the views, so we can't rely on any kind of synchrony. Okay, so eventually, after JST, we hit a correct leader in some view, and then we can terminate. Okay, so this is the high level. So now, next thing I want to do is to design this algorithm. Okay. So if you know Paxos, that's going to help. Otherwise, we're just going to develop it from scratch. It's not that complicated. So I call this algorithm view-based consensus, a kind of a generic view-based algorithm, right? But of course, it's a known thing. It's not something particularly new. Okay, so let's start with something simple. So okay, so we have a view number one. Let's say leader of view one broadcasts its value val to all processes and decides val. Is it the correct implementation? Does it work? Yeah. Yeah, because some process may not receive this message, right? Why? Because the leader may fail, right? So as a result, new view occurs, and then the next leader won't know anything about this message, right? So in one extreme, the leader can just fail straight away, and then after sending, and then none of its messages are going to be received by anyone. Okay. So we have a violation of the agreement. Okay, so it cannot work like this. So the suggestion was that the leader of view one broadcasts a value to all process and then waits for ACKs. Okay. So how many ACKs should the leader wait for? Let's express it in terms of total number of processes n and the failure threshold f. N minus f, I would say. Right? Because where you find another one if f fail. So the best the leader can hope for is to get n minus f ACKs. Okay. Because f can fail, so n minus f is the maximum. Okay, so then important thing is that the leader of the subsequent view need to be able to discover which value was proposed by the first leader, right? So that's something that we need for agreement. So again, the way to do this is by contacting n minus f nodes, because that's the maximum you can contact, right? So for that to work, any two sets of n minus f nodes must intersect. So that means that n minus f is something known as a quorum. Okay. Okay, so we have two quorums of n minus f. What's the minimum size or maximum size of the intersection between two sets of n minus f? It's n minus 2f. Yeah, exactly. So this is just a basic pigeonhole argument, right? You can derive that it's n minus 2f. So n minus 2f must be greater than 0, and then n must be greater than 2f. Okay, so that's a basic condition for this protocol, for any of the partial synchronous protocol to work correctly, including Paxos. Okay, so that was proved to be a necessary condition by DLS, and it's a very valuable exercise to actually try to prove it yourself, right? It's not that complicated, but if you can't prove it, then you can look into the paper. The proof is really simple, right? So if you it essentially goes by contradiction. So suppose we have 2f, right? Then we have two sets of f, right? And because I can only wait for n minus f, right? Which n minus f in this case is going to be f, right? So I can decide on something here and on something else here. Okay, so I can essentially create a disconnection like this. Okay, so that's not a formal argument, but this is more or less how it goes, and you can try it yourself. It's a very good exercise, in my opinion. Okay, so we are going ahead with this assumption. So to simplify things a bit, we just say that n is equal to f plus 1, right? It's reasonable to assume, in particular in practice, why would I have too many nodes if I have only few failures, right? So that I would like to have a minimum number of nodes that I need to tolerate given number of failures, which is 2f plus 1. Okay. Right, so now let's see the full protocol. So this protocol goes like this. Sorry, this is should be 1. This should be 1. Okay. So leader of U1 broadcasts a proposed message with the value, waits for X, and if any process receives propose 1 value, while it is still in view 1, okay, this is important, it stores 1 and val, and it responds with arc1 to the leader. Okay. So once the leader collects n minus f arc1, it can decide val. And then it can also notify everyone else about the committed value by broadcasting a committed value. Okay. So this is the basic protocol for view 1. Okay. But this is also something that we and when you get committed, then you also decide. I just wanted to make one remark. Sorry for that. Yeah. Okay, so this protocol is just a general protocol for committing value in any view. Okay, so as we're going to see in a view greater than 1, the protocol is going to be a bit more complicated. So we first need to find out if something was committed in the previous use, right? And then once we find this out and we discover that something was indeed committed, right? Then I try to recommit it again. And to recommit it again, I'm going to use the same protocol, but I'm going to instantiate it for some other view that I need. Okay. So this 2.5 steps procall, essentially a procall for committing any value in any view. Okay, so let's consider what happens in view greater than 1. Okay. So here it goes as follows. So here that's actually a slight departure from Paxos. So in Paxos, we know that leader first send the message 1A, and then it waits for replies 1B, and so on and so forth. So in view-based consensus, we don't really need to send 1A. Okay, we can just get a notification from the synchronizer for the next view, and then if I am the leader of this view, then I just wait until everyone else send me what we call a new view message. Okay, so this is if you're familiar with Paxos, those are similar as to what is known in Paxos as 1B messages. Okay, so you collect these new view messages, and what you include in these 1B messages is this pair view and value, right? So that you know some previous leader has tried to commit. Okay, so I don't know locally if the value was committed unless I actually got the commit message, but I kind of over approximate, and I think, okay, so that value could have been committed. So I better let the new leader know of that value so that leader won't decide on something else. Okay, so this is what is included in the new view message. Message, and then one important thing is that once process gets this notified of a new view, it won't accept any proposals in any sent in any prior views. Okay. Oh no, sorry. So that's not what is written. No, sorry. Forget about it. So yeah. Yeah, this is just a remark that if I have not, if I'm not aware of any prior proposals, then I just respond with something like this. Okay, so this indicates that's my initial value. So I'm not aware of any proposals. So I have 0 and some null value bottom. Okay. So now again, leader waits for n minus f new view messages. And once it gets these n-f messages, and it's not notified of a new view, right? It would select a value which is associated with the highest view, and then it broadcasts propose. And from this point, yeah, and if everyone responds with this thing, then leader just selects its own value. Yeah, so then I broadcast propose, and then from that point I just continue the algorithm that we discussed before. Okay, so this steps 1 to 4 to commit the value. Right. So this is how the algorithm works. So I hope it is intuitive. So let's kind of briefly convince ourselves that this is a correct, this is a safe implementation of consensus, right? So notice that if there is no synchrony, that this implementation might not be live, right? Because say a synchronizer may keep changing views, so no one is ever able to collect n-f responses, and then there is no any progress, right? But the minimum we want to have is that there is safety. Okay, so we don't violate safety during asynchrony. Okay, so this is how this proof goes, and this is a very common way to prove any or any protocol in this family, including Paxos. So you pick a view v star. It's the minimum view in which some value val star is committed. Okay. So then we prove that for all views which are greater than v star, if the leader of that view adopts a value, some value, then this value is the same as this value val star. It should be val star here. Okay, so that's how it works. So the proof is by induction on all views greater than v star. So initially for v star itself, for the basis, it is clear that the leader can commit at most one value. Okay. Then for inductive step, what we know is that because of the quorum intersection, the leader of some view v plus 1 will hear from at least one process p star that committed val star in view v prime. Okay, so this is by quorum intersection. So then, since we select the highest view, this value that was committed in that view is one of the candidates for selection because it has everything else must have a higher view associated with it. Okay, so but what can be associated with higher view? Now we use the induction hypothesis, and we know that it must be the same value, right? So therefore, this holds, and we have consensus. Okay. So, any questions about this? Yeah.
So after the process commits, it still needs to continue working and continue responding to messages. Is there like some moment of time when it can stop responding to any messages and just finish working?
So yeah, it depends. So if we consider a more general model of partial synchrony where messages can be lost before GST, so there is a model like this defined in DLS paper. Then there is a proof that you can't stop forever, because you just don't know if you're. So essentially, the solution is that okay, I got a commit, I just broadcast commit, right? So if a correct process broadcast commit, then everyone gets it, right? And then at that point, it can stop. So what I can do the same technique as we did for round synchronization. So I can broadcast commit. Then someone who get commit rebroadcast commit, right? That would ensure that the message get to everyone. But that does not work if messages can be lost. So if there is if the network is reliable all the way through, then okay, we can actually stop when everyone gets commit, but otherwise no. Okay. Okay, so this is just the protocol for your reference. So that's essentially, if you're familiar with Paxos, it does look very similar. So first, the leader would wait for f plus 1 new views to see if there is any value to be adopted. Okay, so what is important is that it waits for to receive for f plus 1 matching views here. Okay, so it would ignore messages from any previous views, and it also must be equal to its current view. So when synchronizer switches me to the next view, I need to start ignoring everything that is told that someone tells me from the previous views, right? This is very similar to Paxos. So when I get a higher ballot from a leader, then I stop participating in any previous ballots, right? And this is needed for the safety proof to go through, right? So we need a full quorum locked on a specific value. So a full quorum in the same view to be locked on the same value. Okay, so that's an important part. So essentially, I just to achieve that, I put this condition here. So view is my current view. Okay, so this is something that I get from the synchronizer. Okay, so I got a quorum of f+1 as a leader. I broadcast propose either value that I adopted or my own value, and then I just everyone gets propose, and if they're in the same view, they respond to the leader. Then leader waits for f+1 responses in the same view again. Okay, we need to lock the value in the same view. That's very important. Okay, and then it broadcasts commit message, and then I receive commit message. I can decide as well. Okay. So just have another look on this protocol, because the one for Byzantine failures we're gonna discuss soon are gonna be very similar. Any questions? Make sense? Okay, so we have safety. So now, what about liveness? So liveness depends on the properties of the synchronizer. Okay, so what are these properties? So we need to have this overlap in time. So what should be the overlap that we must guarantee? By how much the processes need to overlap in the same view? You can just say it in words, not to give. You don't have to give a number. So what would be this time qualitatively? So what is the? You said 2 delta?
Yeah, because when the process enters a new view, it sends a message to the new leader, and it should be able to receive the response.
Yeah. So well, but I need to be able to complete the entire protocol. I think it's more, but you're right. You are going in the right direction. So views must eventually overlap in time by the maximum time needed for a correct leader to complete the protocol after GST. Okay, so this is what we need. So then it depends on the protocol how much this time is going to be, right? So for this crash fault-tolerant protocol is going to be we'll see in a moment, but like for a PBFT, it's going to be a different value. For hot stuff, another value. So it depends on the protocol. Okay. So, but qualitatively, we can say that must be sufficient to commit a value. Okay. So the synchronizer specification kind of is set up so we can achieve what we need. Okay, so this is the specification. So we say that there exists some, this curly v, a view curly v, and a constant d such that we have the following properties. So all correct processes enter this view v after GST, and then for all views greater than this curly v is entered by all correct processes. Then we have a property which is called bounded entry. So if a correct process enters some of these synchronous views at time t, then all correct processes enter v no later than t plus d. Okay, so bounded entry essentially captures this idea that we have seen that there might be discrepancy in time at which different processes enter the same round or same view. And this discrepancy would depend on the round synchronization protocol. right? So for crash fault-tolerant protocol, it's going to be 2D and 2 delta, and maybe for other protocols can be something else, right? So this is bounded entry, and then there is a property called a minimum duration, which says that for all these views after the synchronous views, the first process to enter this view must stay in this view for at least timeout. Or timeout is a parameter of the synchronizer. Now, if we have this abstract specification, and then we produce a synchronizer that satisfies this abstract specification, then we essentially know everything we need to know. Okay, so to have a live consensus protocol. So we look at this example. So here we have before JST, we have processes in many different views. Okay, so the first property ensures that there is this view that everyone enters, every correct process enters after global stabilization time. And then we know that every subsequent view is also entered by all processes. This is important because we want to rotate leaders, so we want at some point get to the correct leader, and that leader could terminate the protocol. Okay. So then bounded entry ensures that the width of this yellow part is less than, let's say, should be D. Okay. And then I forgot how to call it. So minimum duration property ensures that this is at least timeout. And if we have a synchronizer instantiated appropriately given this constant, then we know that we can compute the size of the overlap. So this is the overlap in this case, which is going to be at least timeout minus delta. So for this, for a VB consensus that we discussed, this timeout is going to be 5 delta because we need sorry, it's yeah, I had to be more precise here. So it should be, so because this is not delta, this is D here. Okay, so because we're talking about the specification, generic specification, so it should be 4 delta plus D. Okay, so we know that for the synchronizer that we implemented before, D is equal to 2 delta. So we have 4 delta and 2 delta, so we have 6 delta, right? So that's we need to initialize synchronizer with timeout 6 delta. Okay. So if we have 6 delta, then VB consensus is guaranteed to eventually terminate, right? So this follows from so first from progress 1 and 2, we get that we eventually get to this curly V that everyone is entering, and then every view after that is being entered by everyone. It means that eventually some correct process would become a leader of one of these views. And then they need to overlap by at least 4 delta. So from that, so we know that this 4 delta plus D, and assuming the synchronizer that we discussed before, it give us 6 delta. Okay, so in this view, the leader is correct and gonna be able to reach consensus. Okay, so this essentially shows that how to use the synchronizer, so how to use the abstract specification of the synchronizer to derive liveness of view-based consensus. Okay, so you already have a blueprint how to design a live consensus protocol for partial synchrony. So you have a synchronizer with the specification that I described in the previous slide, right? Then you have a safe protocol for a single view. Then you combine these two things together and you get live and safe consensus protocol. Okay. Yeah, so essentially, as I mentioned before, to build a synchronizer for this view synchronizer for a crash fault-tolerant system, crash fault-tolerant partial synchronous system, we can just reuse the broadcast synchronizer that we discussed before. So here's full code, but this is just essentially, I just replaced rounds with views. We're also going to assume that phi is equal 1 because it does not matter anymore because at GST we can accumulate arbitrary drift anyway. So I need to be able to tolerate this drift even if phi is equal 1. And but if I wanna work correctly with the arbitrary phi, then I just need to multiply this by phi here. And that would give me the solution. Okay, so before I proceed to Byzantine view synchronization, are there any questions about?
What's an example of partially synchronized system?
So any practical system can be reasonably described as partially synchronous.
Yeah, but I guess every practical system is like asynchronous.
If it is asynchronous, then if it is always asynchronous, then we probably won't have Bitcoin, we won't have Ethereum, we won't have Raft, because consensus is impossible in a synchronous system.
So I think that most real-time systems, they are like there isn't some specific goal stabilization time after everything.
Yeah, of course. Of course, but I think so. If you agree that there is a time where there are some sufficiently long periods of time when system is okay, right? Then this is practical, right? So this is something practical, right? Would you say this practical? So this is complete asynchrony, and this is synchrony, and again. Would you call this practical? So if this is practical, then this is identical to just partial, like formally defined partial synchronous system. Why? Because I don't know what this time is. Okay. I can't design my when I design my algorithm, I have no idea what when GST is going to occur and if it occurs. So I design my system without this assumption. So that means that first I never violate safety. So I always preserve agreement, no matter what, if system is asynchronous or not, right? And second of all, I know that if system is synchronous, then I need to do my best effort. I need eventually to terminate. That means that I need to make best effort to drive system to termination, right? So if this is how I build my system, then I would essentially ensure that if this period of time is long enough, right? In practice, it's not going to be forever, right? It's going to be for some limited time. When it is long enough, then I would terminate. Okay, so that's the rationale for partial synchronous systems. That makes sense. Okay, so in partial synchronous system, they very convenient for say more theoretical mathematical analysis. So this is kind of very nice thing about them is this is where practice and theory converge, right? It's a nice thing, right? Right, so let's talk about Byzantine view synchronization. Okay, so Byzantine model I've already defined. So we have, again, we have a complete network of n nodes. We have threshold f of process that can experience Byzantine failure. So Byzantine failure means that Byzantine process may behave in arbitrary way. So it can crash, it can omit messages, it can deviate from its protocol, can do anything. Process that never fails is correct. So that's as before. And due to the lower bounds that I mentioned before, so we can't hope to achieve deterministic consensus with Byzantine process even in synchrony if we have less than 3F processes. So for that reason, I'm gonna assume that we have n equal to 3F plus 1. So it's the minimum number of processes required to tolerate F Byzantine failures. Okay. So this is the Byzantine failure model. So a nice thing is that we already have a solution for Byzantine synchronizer. So how we obtain solution for Byzantine synchronizer? We take our broadcast synchronizer from before, and we replace, so where we received message from 1, we wait to receive messages from f plus 1. And where we wait to receive messages from f plus 1, we wait to receive messages from 2f plus 1. That's the only, really the only modification needed to obtain a Byzantine fault-tolerant synchronizer from crash fault-tolerant synchronizer. Okay, so this implementation has problems with performance. So this is we'll discuss them in the next few slides, which actually motivated us to improve that. But as someone said, the most difficult part is to go from no solution to a solution, right? So now we have a solution, right? So this is so we can synchronize views in Byzantine fault-tolerant system. So why this is f plus 1? Simply because in a Byzantine system, if I just get a message from one process, I can't tell if this message is good or bad, because that process can be Byzantine. So for that reason, I need to wait for f to receive f plus 1 copies. Okay. And if I received f plus 1 copies, then I also gonna vote for this view myself, right? So this way, I kind of propagate. I boost the propagation of the new view. Okay. So here I wait for 2f plus 1 to get to the next view. And why I wait for 2f plus 1? Because if I got to f plus 1, then I know that f plus 1 supported that view, right? F plus 1, there are f plus 1 correct processes that supported this view. Okay, because I have 3f plus 1 in total, right? So if I get 2f plus 1 copies, okay, I can subtract f again, get f plus 1 copies, right? So f plus 1 must be from correct. If I have f plus 1 from correct, then these f plus 1 processes would eventually persuade everyone to rebroadcast this message, and then I will get to f plus 1. Okay, eventually everyone gets to f plus 1. Okay, so this is the technique to achieve it. So some of you might be familiar with the thing called Byzantine broadcast or BRCA broadcast. So this is very similar to how that works. Okay. So this synchronizer was first proposed by Naor, Boudet, Malhi in 2021, and in the Cogsworth paper. So it has d equal to 2 delta. It's 2 delta because we essentially have the same message pattern between this one and this one, so it's still 2 delta. So I assumed phi equals 1 for simplicity, but you can just multiply this by phi. if you want to support any other fee. What do you think? Yeah.
What do you expect potentially of the process? The thing is, you like expect them in any order, and like the fault process may be last in the sequence of single message, and you may process B from fault process. Is this an issue?
I don't see any issue with the order in which you receive messages because you.
I mean, you can process only one B.
Yeah, but so this entire code only executes if this condition holds. So okay, so what you are saying is a great observation that there are some cheating going on here because I don't actually say that how I accumulate these messages, right? Right, but this you can imagine in the background, I have some buffers where I store these messages, right? So and then I have some hash table. So actually, I'm going to discuss this in I think in the next slide. So that because this is one of the reasons why this algorithm is inefficient in terms of its space complexity. Because for every message I receive and for which I have less than f+1 copies, I need to remember something about this message. I need to remember that I received this message, right? So before JST, I can receive many large number of such messages from, say, Byzantine nodes, which actually never gonna be used, never gonna be supported by correct nodes, but I still need to keep them. You know, I can eventually garbage collect, but in theory, my space is unbounded here because I need to remember all these messages. No, it's not. There is no last. It's just a predicate, right? For each, so I have some hash table from views to a number of sync that I received, right? So this is one implementation that I have, right? So when I get a message for view V, I just update this counter, right? Well, I need to also remember that I should not update the counter twice for the same process. Yeah, okay. So things like that. So I need to do this counting in the background. So once I have for some view, I have some view maps to the value f+1. Then this condition becomes true, and then this this code is going to be executed.
So you don't like use wizard for set. You just use your counter as some sort of.
Yeah, I just keep I do bookkeeping, right, of these messages in order to. I need to validate this predicate, right, and I need to validate this predicate. So I need to do some bookkeeping, which is not shown here for simplicity. Right? Okay. Okay. So there are a few problems with this synchronizer, which we addressed in a paper in 2020. So exactly what been remarked here is that Byzantine nodes may attempt exhausting memory of correct nodes by issuing large number of things for future views before JST, which everyone has to track, because in case these views would be complemented to the desired number f+1 or 2f+1. Okay. So if you think about it, they can actually cause denial of service by doing so, right? So they can essentially exhaust the memory of correct processes through this attack. So the question is if we can bound space complexity. So another possible attack the Byzantine nodes can mount, they can withhold some things sent before GST and then schedule them after GST. So we may have a situation where there are some, let's say, we have F processes who are correct, okay? And they got to some very, very advanced view, but because messages are being delayed, they can't yet proceed. And then we have the rest of the process, which include Byzantine processes, which kind of hold back with the older views that they entered before. And then after GST, they can just start showing these views one by one, essentially causing everyone to enter lots and lots of obsolete views. Okay, so that's another problem, and the problem with that is that our latency can be unbounded unless we are not careful. Okay, so we would like to bound the latency of converging to this good view, the first good view. And we also want to tolerate message loss before GST. Okay, so if you think about it, just in a partial synchrony model where messages before GST can be arbitrarily delayed, the question is what is guaranteed about these messages that are sent before GST, when they can arrive. So we can't. So some papers assume that all these messages can arrive within some. Within delta after GST, but that's a not very reasonable assumption because the number of such messages is unbounded. So to guarantee something like that, we need to say that we essentially it's amount to saying that we can process unbounded number of messages in a bounded time. So therefore, it's much more reasonable to assume that messages can be lost before GST, and then we have to deal with that. Okay, so this is the assumption that another assumption that we want to support. So naturally, that makes algorithm much more robust. So the previous algorithm that I showed to you, it does not tolerate message loss before GST. So the messages must be reliable at all times. Okay. So these things are nice to have. So one last thing that we also want to have is to remove this dependency on known message delay, delta. Okay, so you remember that previous synchronizers, in order to use them, application needs to plug in the message delay to calculate the timeout. So the question is if we can do without that. Okay, so that would be also nice. Okay. So that, of course, affects the specification of the synchronizer. So but it is essentially exactly the same as before. But now, let's say I replace a fixed timeout here with some function of a view. Okay, and I just say that this function grows monotonically with views. Okay, so this way I can have an algorithm that, say, consensus algorithm that can adapt to any specific timeout, any specific message latency without really knowing it. Okay. So this is how I modify the specification. Of course, this will also affect the implementation of the algorithm. Okay. Right. So now I'm gonna describe a synchronizer which is called FastSync, which meets all these properties that I presented before. Sorry. So I'm not gonna show you the code. It's a bit complex, but we will discuss the main ideas. So upon entering a view, now I set timer for not for a fixed timeout, but for depending on this function that I was instantiated with. So examples of this function can be, for example, exponential function, or exponential function makes sense to use because it grows very fast. And when timer expires, I try to switch views. Okay. So how I switch views? So this is a departure from the broadcast synchronizer that I described before. So now I'm worried about running in bounded space. So instead of kind of having under the covers maintaining this say hash table that maps from views to does this bookkeeping for all the views that have been received, I replace that with a very explicit data structure. So I just have the for each process. Say we have, so in this example, so we're going to use f equal 1, and then n is equal 3f plus 1, 4. Okay. So I have an array of 4 entries, and what I remember in each entry is the maximum view that this process send a sync message for. Okay. So this is my main data structure. So now, when I enter a new view, so instead of doing entering on receiving matching views, I do this based on receiving non-matching views, but I do the following trick. So when I receive 2f plus 1 syncs for views greater than a specific view, okay, then I enter the minimal view in them. Okay, so why I can do this intuitively? Because I know that all processes enter at view which is at least that high. Okay, we will see some picture, it would be clear. Okay, so this allows every process to quickly catch up and without going through some useless views in the meanwhile. Okay, so here's the example. So if this is the situation we have, then we take the view such that we have 2f plus 1. So 2f plus 1 here is 3. So at least 3 processes entered view higher than my current view. So let's say my current view is 15, right? So now I see that at least 3 processes entered view 20. Okay, why? Because this one is 20, this one 20, this is 50. Okay, so definitely this guy have bypassed 20. So it's safe to enter 20. Okay, so this is 2f plus 1. Say that they vote for view at least 20. Okay, so if 20 is also greater than the view I'm currently in, then it is okay to jump directly to this view, okay, and catch up with the rest. Now, I can do the same thing for f plus 1. So I have remember I have f plus 1 criteria, I have 2f plus 1 criteria. So I also do, so on f plus 1, I do relaying, okay. So I use the similar rule for determining when I can relay. But now I am doing this f plus 1's highest, right? So before that I did 2f plus 1 highest, now I do f plus 1 highest. Okay. So if I have, so now again, so to remind you, f equals 1. So f plus 1 is equal to. Okay, so if I have this situation, 20, 50. Okay. I know that there is at least one correct process that entered view at least 20. Okay. And if I have not yet voted for this view, if I only voted for lower views, then I vote for view 20. Okay. So this is exactly the same thing. Okay. So this is so essentially, if you think how we can modify the broadcast synchronizer, this is what we do. So we have this array, then where we have a condition for f+1, for f+1 matching, we replace this condition for f+1's highest in the array. Okay. When I have a condition for 2f+1 matching, I replace it with the condition for 2f+1's highest. It's essentially the only, say, important and interesting modification of that algorithm. So in many other aspects, it's more or less the same algorithm. Okay. So that's the idea. Okay. So here I have some example to kind of contrast what could happen with how we can act on inconsistent views, on mismatching views. So so let's say this is the situation that we can get to after when GST occurs. So we can have say two correct processes here, and they just been stuck in view 1. Why they been stuck in view 1? Because no messages from these processes been propagated to the rest of the process. So they essentially partitioned from the rest of the system. Okay, because of the message loss. Now we have here on the other side we have this this f+1 process reaching view 9, and so now they're voting for view 10. Now what these guys can do, these two bad guys, they can essentially support these processes and then allow them to enter view 10, and they can essentially just cause them to enter any view they want, and then some process here, say, can attempt to enter view 11 here. Okay, so we can end up in this situation where we have a large number of mismatching views, and this is something that broadcast synchronizer can't cope with because of the message loss. So it will get stuck in this situation. But the synchronizer that can act, so fast sync synchronizer that can act on mismatching views, would be able to get out of this situation simply because these guys, the moment they hear from these correct processes, they would be able to jump directly to 10, because 10 is simply, in this case, a view that is entered by at least 3, which is f+1, right? And then from this point on, they can just all synchronize on the same view. So they all gonna time out on 10, propose 11, and then they synchronize in view 11. Okay. So what about the latency of this algorithm? So we said, okay, so we solved the problem of unbounded memory. We solved the problem of message loss with unbounded memory. Now, we also wanted to have bounded latency. So bounded latency, say, we can analyze in two cases. So one case is a good case. So under a favorable condition, all processes, they start after GST. Okay, so we start directly in the synchronous system. So in this case, everything happens very quickly. So the moment the last process joins the protocol, we have 2f+1 sync messages for view 1, and then everyone just synchronizes in view 1 in time delta. Okay, so this is nice. So if we have a situation where the processes start before GST, so there could be some mismatch in views here, then we can also bound this time from GST to until everyone. So this elast means everyone enters this first good view. So in this case, we can show that this first good view is the maximum view at GST plus some retransmission period, which we need to tolerate message loss, +1. So this view is going to be, this latency is going to be retransmission period plus the timeout in the view before the good one, plus 3 delta. So why it is 3 delta? Because this is some process wants to advance to the next view, then it sends a message, then another 2 delta is needed to get to for everyone to get to that view. Okay, so we also have a nice bound here. So let me just summarize fast sync synchronizer. So it is correct with respect to the specification that I showed. It runs in bounded space always, including before GST. It has constant time complexity after GST. And it tolerates message loss before GST. And with this synchronizer, we were able to write simple code for these modern consensus algorithms, including PBFT, hot stuff, two-phase hot stuff, which is essentially identical to Tendermint, SBFT. So the results are, so you can find this in the paper. Okay. So this is the PBFT with the synchronizer, just to give you some taste. So here I got a bit lazy and I didn't write the pseudocode from scratch. I just took it from the paper. So essentially, we have this. It's very similar in nature to the VB consensus. Okay, but the main difference is that here, when I say when leader sends propose, everyone who receives this propose, they also want to. They don't accept it immediately. They also want to rebroadcast it, so they can validate that this is a correct proposal. So everyone can validate this is a correct proposal. So there's results in an extra phase here, essentially needed to prevent equivocation by Byzantine leader. Other than that, that's essentially the same algorithm. So it assumes message authentication. So you can imagine this view-based consensus plus one more phase to validate the leader's messages. So this is kind of the message pattern of PBFT. So first is all to leader, then we have all to all, all to all, all to all for the remaining phases. So in total, this is 4 delta. Then given that for delta, we can plug it into the properties of the synchronizer, and then we can analyze the latency of PBFT. So I'm not going to go over this. This is a bit some maths here, but you will find the details in the slides and in the paper. But important thing to remember is that with the synchronizer, we have we have very well-formed guarantees as regards the latency. Then if we combine it with the consensus algorithm, we can also derive the latency bound for consensus. Okay. So last thing I want to mention briefly. So this is the paper from 2022 that essentially generalizes the view synchronizer idea for state machine replication. So we can implement state machine replication by repeatedly calling consensus as a black box, so we can essentially reuse the same solution as I presented before. But this would be suboptimal because in many situations we would like to reuse the same leader across multiple consensus instances. So we don't want to change the leader every time we change the view. So to support that, we designed a new kind of synchronizer. So this is called SMR synchronizer. So that that is in the paper from 2022. So in the SMR synchronizer, in addition to this new view indication, there is also the advance request. So advance request is issued by the application, such as state machine replication. Okay, so that requires that the application monitors the situation, so it sees that I know if everything is okay in the specific view, or maybe we are not getting messages fast enough. So if that, or maybe a leader stops sending us messages or things like that. If it detects things like that and would issue the advance request, and then only then view synchronizer will execute this protocol. It exchanges some messages, f+1 to f+1, and then it produces a new view. Okay, so that results in much more, say, elegant and efficient implementation of state machine replication, because we essentially only need to synchronize when it is really needed, right? But maybe a slight downside is that now application needs to be able to detect the situation when it needs to resynchronize. Okay. So so this is this SMR synchronizer. That brings me to the conclusion. So what we presented is the modular framework for consensus state machine replication, which is based on synchronizer abstraction. Okay, so maybe the second part, so the Byzantine failure part was a bit daunting, but I hope that at least the crash fault-tolerant part was enough to convince you that this is a nice framework and you can easily use it for designing consensus algorithms and state machine replication. So this is the picture to remember. Okay, so there is a view synchronizer. There is a state machine replication or consensus. Essentially, you can have one synchronizer which just produces new view, or you can have a synchronizer that application dependent that also can produce this advance request. So this, I hope I convinced you that simplifies design of provably correct consensus and SMR protocols, facilitates their performance analysis. Okay, and we actually keep discovering new applications for the synchronizer. So just the latest one is just was accepted to Oporis 23. So that's so here we designed a synchronizer which is able to cope with adversarial message loss and network partitions. So yeah, so that kind of shows that this abstraction is useful. So it's useful in crash fault-tolerant setting. It's useful in Byzantine setting. So this is the new setting that where we have a network which misbehaves. So essentially, here we have a Byzantine network, right? So how we can deal with Byzantine network. Again, we can design a synchronizer for this case. All right. Thank you very much. Any questions, please ask.